Welcome everybody. In this video we'll be going over task 8 of the NSA 2024 Codebreakers challenge. This task 8 is a little bit longer than the other tasks, so this might take a little bit, or take a couple parts to go through the reverse engineering and talk about the cryptography aspects of it. But in task 7 we were tasked with identifying different IP addresses on a network that were had communicated with the C2 server, and we did that through a file directory traversal kind of misconfiguration in their binary. In this one, we're going to be decrypting the comms. So with that, let's just hop right into it. So the security team at Blue Horizon Mobile was able to capture a packet destined to the device under investigation. It looks to be encrypted, and a quick analysis of the firmware shows it uses an HMAC scheme for authentication. Can you decrypt the packet and recover the HMAC key the software uses to verify the contents? So this challenge gives us one file. It's a packet capture, so a PCAP. We're going to download that. And then what the challenge wants us to do is enter the HMAC key string used to authenticate the given packet. So if we remember back to an earlier challenge, when we were looking through, I think challenge 5 or something, when we were looking through the config within agent, we had identified that there was reference to an HMAC file or key file, but on our system, compared to the other files like the private keys or something, we were not actually given the HMAC file. So this is where our challenge is going to take place. We're going to try and identify what's in that, or what should be in that file, and see if we can decrypt the packet. So with that, I'm going to come over here, create our challenge 8 directory, copy over the packet capture, and then I'm going to open it up, see if that opens it. Okay, so it opens up in Wireshark. Looks like it's just one single packet. The source is the 193.995.217, which was one of the identified devices in the IPs that we had in the list from the last challenge. The destination 176.241.182. I don't think that was the C2. It might have been. Can't remember off the top of my head. But it looks like it just has a list of bytes. So if we actually look at the data, 288 bytes are sent, and then apparently it's encrypted in some sort. We just need to find out how it's encrypted. So to start off, let's pull this data out. So I'm going to do follow UDP stream, and then I'm going to set this to raw, and I'm going to save that as data.raw. So this should come out just as the raw data blob within our directory now. So if we do xxd of data.raw, we can see it's just the raw bytes. So 6b17, d1, f2, e1, 2c, and so on. Just looking at it, we could check the entropy. I think entropy is the command, whatever. But just kind of looks like random data for the most part. Overall, we kind of just need to figure out a way to decrypt it. So if we think back, we don't really need Wireshark open anymore. I can close that. All we have left is the agent file, really. We've already identified what the dropper and the diagnostic client were communicating and connecting to. Didn't appear that there's anything else in there, but if we think back to the command thread within the agent file, we knew that it was creating a socket, it was listening on that socket, so this could be where the data is actually sent, or sent from. We read from the socket, and then we do a decryption of some sort. As we had identified, we also open up a file, so maybe if we step through this, we can see what file is actually being opened, then we can see what kind of data is actually being decrypted. There's a good chance, just based on this read from socket file we had identified, if we follow the parameters, local 804 appears to probably get set within the setup socket and bind, so that might be just the socket. The osstack 368 gets used down here in the decrypt function, and then local 800 also gets used, so there's a good chance local 800 is probably just the size read in, and then this is probably the buffer that it's read into. 0x360 could be the number of bytes that it max bytes read in, 0xA0 could be like a secondary decryption key of some sort. We're not sure. We didn't really look through that function too much. But if we look up here at buffer again, we can see that it's 364 characters in length, which actually lines up really well with this 360, which happens to be 864 as well. So there's a good chance that 360 is probably the max size read into buffer, and size is just going to be the number of bytes that was read. So there's no guarantee. We could check to see what param3 would be. Just follow that. Maybe it's just checking to see if data was actually read in of some sort. Maybe that could be a minimum size that has to be read in. So maybe there's a minimum and a maximum size. It won't be too far off. Other than that, we kind of just need to hop in and try and figure out what we're working with. So first, let's try and figure out what file is being read. So we know a file is being read because we identified that an open system call was being, or a read system call was being done here after an open at and a stat to make sure the file exists. So it doesn't hurt for us to actually jump into this function and walk through it. There's a couple ways we could do this. We have the original QEMU instance, the QEMU system running the entire virtual environment still. That one, it could be of use to have us walk through it, but it could be a little bit cumbersome to kind of start up and stop every single time. So another way we could do this is just run it locally again. I'm going to just copy over the files we need from 5. Just copy over agent, actually. Copy this whole directory over so we don't have to keep going back and forth. We could just run it locally within just QEMU arch64. Last time we had done this, we just connected GDB to it. We had identified that when it gets to the threading part, just within the QEMU user space instance, that it struggles. So that's not a good long-term approach. The approach we're going to go with, if we go back to main, is we're going to actually binary patch this file so that, because we don't care about these collect or upload threads, all we care about is the command thread. So we're actually going to patch it so it doesn't use threads anymore and just calls command thread with the correct parameters. For that to happen, we need to step through it at least once to see what command thread should be. Actually, we don't really need to because we know command thread is the function we're going to be calling, and then pthread create always passes in the arguments within this point, so in the fourth argument. So we can just patch the binary to say, instead of putting command thread into x2, we just call command thread, and then we move x3 into x0. So not too bad of a patch, but not too easy either. So I'm just going to come in here and do a quick patch instruction. Instead of branch and link there, I'm going to actually do branch register. Actually, let's do branch and link register. x2. This way, it just branches and links to x2. We don't really care that x2 is corrupted at this point, because x2 would just be set to command thread. We could even do x20. Doesn't matter too much. x0 here, instead of moving x0, x26, which would be our thread number, we're going to patch this with moving x0, x3. This way it moves the parameter within local 1088 or whatever's in there. Should be like a list of pointers of some sort, as we had identified with the previous functions. One other thing that we'll need to do is make sure we knock these two functions out, because otherwise they could cause some problems. Edit, nope, not edit function. I'm going to patch instruction. Just going to say nop here. Oh, it doesn't like that. There you go. Nop there. Patch this instruction as well. Put this to nop. Oh, not 0. Nop. It doesn't matter too much or at all that these registers are set to something and then we don't actually use them. We could nop out this whole block, but that could be, we could accidentally corrupt a variable that gets set that we might be missing because we're not looking too closely at the assembly. With this, I haven't used Ghidra's export often. I wonder if it's possible to use this. Yes. It's been a while since I've exported through Ghidra, so I'm going to see if this works. A destination file is home Kali agent. Go check that guy out, see if it even runs. Kali. We have a file here, agent. It says it's an executable, so chmod. Let's give it all permissions. I'll actually move it into our directory first. Codebreakers 8. Agent. I'm going to rename it to agent_test, just to make sure we don't overwrite. Whoops. Overwrite it. The original one. So here we should have agent test now. We'll try running this. Arch 64. We're going to do tech G1234 because we want to connect GDB to it right away. Agent_test. And then config. GB multi-arch on agent test. We can do target remote 1234. It did connect. We'll check this address out, 400 BC0, just to identify that we're actually in something correctly. 400 BC0. It looks like the first instruction should be a NOP, so probably just in the start. So everything does look correct. Let's go to command. Let's go to main actually. Main.main. Oh, not main. We're on Go binary. We'll come down here and we'll set a breakpoint at this command thread. So at 408B8, we'll set a breakpoint there. 408B8, continue down, and it looks like we have a branch X2, so, and we could check RDI, or X0 I guess in this case, using ARM. And it does appear we have a structure of some sort. We could check to see what these parameters are, because it appeared that most of them are all different. That one is empty. This one's 0.0.0. Can't access that one. That's interesting. Maybe it's just a string itself. Should be at 40. That doesn't look like a string. Kind of looks like an address of some sort, but the addresses are, it's a little bit lower in the realm. I don't think I can via, oh, I can via map. I think this might just be the ChemU. Oh, it didn't. Nice. It should be in this range, I think, for E2. Nope. Yeah, right here. Should be in this one, which says it has no permissions, so maybe something is mapped there that we just don't have access to, or unmapped at within one of these load config files. Might not be anything important. Could be shared memory between threads, and since we never actually initiated the thread calls, maybe it doesn't get set up correctly. That's just a hunch, but we could just step through it and find out later maybe. So if we step into this function, we should be within command thread. Param1 should be a pointer, and if we actually follow, we can start looking at some of the arguments that should be within param1. So if we come down here, param1 plus 2 plus 50, or param, well, we actually really only care about this function. So if we set a breakpoint down here at 401, we can see what file is trying to be read. 401.3fc. 401.3fc, continue. Doesn't look like anything's happening because it's never going to be hit yet. Because remember, it's actually going to set up a UDP listening port. So we need to netcat to localhost tacu, I believe, tacu on port 9000. If we send some data, we forgot to set the I'm not sure if this one actually had any verbose. Nope, debug should be set within the config, so that should be fine. So if we just send some data, it says receive 22 bytes from our address. It didn't say anything connected because UDP is kind of a stateless communication. If we go back to GDB, we can see we actually hit the breakpoint. And if we look, x1 is going to be the second parameter, so it must be the file that's opening, and that's going to be the HMAC key. So it looks like right here we're actually reading in our HMAC. So read HMAC key. So that's good to know. Param1 could be where it's being stored. We're not really sure what's there right now. We could check to see what it looks like in memory. I would guess that this is just where the HMAC is being stored. We don't know what the length of the HMAC is, but based on the fact that there's 64 bytes of zeros right here, maybe the HMAC could be up to 64, could be 64. Unlike the private key or the ID that we had identified, the UUID we had identified earlier, we don't know what the file size is because we don't have a file to work with right now. We could look through read HMAC, see how many bytes it's actually reading. So does an open at, does a do while read. So while LVAR4 is less than 58, 58 is malloc IVAR1, just says it's malloc to the size 58, but it doesn't appear to be set anywhere. So this could be Ghidra misidentifying something. Could also just be set right here within the stat. Stat could it usually returns a structure of some sort. So it could be stack. This stack variable is being identified a little bit incorrectly, it looks like. So maybe malloc 58 is being set within the stat, so maybe it just reads in however many bytes are within the file. So we don't really know what's there yet. Failed to read file is probably what's going to print after this because we don't have the file existing. So let's just continue through and see what happens. Yep, failed to read file. So stopped command thread, starting command thread, listening on port 9000. That shouldn't happen, I don't think. It's weird that that started and stopped again. Because I don't think it should have. Oh, maybe it just actually breaks out since it didn't read the file. Yeah, because this should, yep, it breaks out. So there should be a while loop that reads forever, or reads from the socket as soon as it gets data. It's interesting that it started back up because we had made this a call. So we go back to main. It should have exited this function, which it appeared to be, or paired to. And then it should have came down and just left this function down here. Just gone through. So at some point we recalled command thread, which is interesting in itself. But let's just add a test HMAC file. So let's edit our config. Where's config think it's going to be? Config thinks it's going to be in the same directory, so that works. Let's just echo, we'll do a bunch of A's to HMAC underscore key. Just looked at it, I forgot. Yep, HMAC underscore key. So this time, when we send data, do a bunch of A's again. This time when it reads it in, if we save this directory, I'm not going to actually step through this file or the function, I'm just going to step over it. We can check in memory and see that it read in our A's into that memory spot. This time it shouldn't fail. It shouldn't fail within the, let's go back into command thread. Shouldn't fail at this part right here. We should actually step through further. So now we can go down to the string length and see what it's string lengthing. And get a comparison to what's happening down there. So if we step through, we come up to a function call, 12E0. It's good to identify where it's being at. We think it's the string length call. It is not. 12E0. Go to 4012E0. Looks like we jumped back up to the top. So something happened incorrectly. So we know we should have gotten past this one because data was read in. But what about this IVAR2? IVAR2 must not have passed, even though it looks to be set after you read data from socket. And we didn't probably send in enough data. Probably needs to be at least A0 bytes long. So let's continue again. The breakpoint at the HMAC file should still be there. This time let's just send in enough data. I think our connection might still be stable, so I don't need to close this. It did, nice. 274 should be enough bytes. We step through it. We could check the compares. It shouldn't matter too much. Now we have a check rate here at 4014F8, which if we come down here should be the string length call, which it is. So it looks like string length is comparing our length read in, or from the HMAC key. Looks like it's reading the comparing from the HMAC key, or it's finding the length, but it's also passing 0x40, which is 64. So maybe it's a string max length kind of function, so string end length. So if it's too long, end length, it won't read in all those bytes. So if we press enter, we should identify that. Don't need this one anymore. If we do next instruction, x0 should be the number of bytes we sent in, or is in HMAC key. And it looks like it's 12, so that should be string end length. Then we step into decrypt. I'm going to step over here. I probably won't step into it yet. I just want to see what the arguments are. So it looks like argument 0, argument 1 are both empty. That could maybe be the final location that values are to be stored at. x2 is a very long string that's all A's. 273 times just happens to be the number of bytes we sent in, minus 1, so accounting for the new line, maybe. Maybe they could have added a null byte of some sort. It's weird that, because 274 should include the new line, but this also includes, 273 plus 1 bytes, 274. Yep, so that's going to be our data. 112 is just going to be 274 in hex. This is just the letter N, so we're unsure what that is. 4E, it's not a size we know of yet, so it can't be that. 0x5 is going to be all A's, or which is going to be the HMAC key, so that's HMAC key size. x7 is empty. If we check back here to see how many arguments there are, 0, 1, 2, 3, 4, 5. Looks like x5 might be the last one. Oops, didn't mean to step into that function. Didn't mean to step into it again. So x0, x1, 2, 3, 4, 5, 6. x6 appears to be the last one, so x7 doesn't actually matter. So this one's useless, or not useless, but just not needed. So we are so far haven't identified x4 and haven't identified x0 and x1. But in here we can rename some of these variables now. Going to open this up. Going to put it off to the side for now, just so we can get it viewing. I thought this would maybe make it look worse, but it's kind of the same size as it always is, so it doesn't matter. So we don't know what x1 or x2 are, or x0, x1 are. x2 appears to be our socket buffer. Looks like the socket buffer length. We don't know what that one is. That's just 4E. Maybe it's a size of some sort. We're not sure. x5. Change this one to HMAC data, and then HMAC data length. To help identify some of these parameters, we can identify where they're used last. Param1 appears to be used within this function and this function. Doesn't appear anywhere else. Param2 is set to socket buffer length at the end, and it's just dereferenced and set, so this appears to be some kind of size, so maybe ending size. So param1, based on this kind of analysis, there's a good chance that since it's also using socket buffer length, that param1 is going to be our ending buffer. So after it's decrypted, we could step into this function and maybe identify it. Went in on param2. While param2 plus param3, which is the size, is not equal to this counter. pvar3 is also set to it. Grab the characters. Do something with the characters. Plus 200. Not really sure yet. But for now, we can call it ending buffer. Param5, we're still not sure about. Can see that it's passed in with the socket buffer into this function. The param2 looks like it's passed into this function. Was that param1? Nope, param2 still. Then we just grab the bytes, shift them left, or them by another value, and store them back. But the fact that we're dereferencing it means that it's some kind of pointer and not with a counter. We're dereferencing it with a counter of some sort. That identifies that this should be some kind of string and not just 4e, so maybe we didn't read all the data in, so we maybe should follow that backwards and see where the data actually comes from. So 0, 1, 2, 3, 4, it's right here. So param1, it's coming in through parameters. 1a, is that used anywhere? 1a is not used yet, but if we follow the parameters, do I have the parameter structure easily available? I can try to identify what register it comes from, because it might still be in that register. So if we come here into the assembly, it looks like it's grabbed from x20 plus 1a. So if we just check what's in x20, this appears to be our original structure still. Plus 1a. Oops, not equals, plus 1a. Oh, I just overwrote it. Let's set that back, because I'm pretty sure x20 is now overwritten on accident. Let's just set that back to this address. x20 plus 0x1a puts us at this location. So it looks like it is some kind of string. So maybe that's why this one didn't work. So maybe the 282e is something else. And then there's another string right here. But we need to figure out what kind of strings actually should be there. So let's go back to main. We need to identify what's sent in. And we know local 88 is sent in, but where is it set? Local 88 is set with this value, which doesn't appear to be anything. Local 1088, is it set anywhere else? 1088 doesn't appear to be really used anywhere else. What about the other values around it? Since we know it's a structure, so 1088 would be here. Oh, if it was the address, that's actually just a pointer to there. 1088 at 0 is set to this value, which is probably 5. It's weird that 1088 is accessed like this and not like the others. The others were set as the address of those values, whereas 1088 is just directly set as a... Oh, it's currently accessed as an array. So then 1088 at index 1 should be accessed somewhere also. We could just increase it because we know it's going to be a array of at least kind of 4 and see what else is used, but there's a good chance that this value right below it is then set, and then maybe this string of 10 kind of looks value or valid for this area. So 1080 is set to a pointer. Pointer is used within the SSH private key. That one doesn't really sound right. Might be going the wrong way. But we could check to see what 1078 is. 1078 command host. That one does sound a little bit better in the fact that if we check out what's at this location, we know it's 0.0.0. And if we check our config, 0.0 is command host. So we're kind of narrowing it down. So then maybe this offstack 10.6e should be this last pointer. It looks like a read private key. And remember, a private key would be that ECC key. So there's a good hunch that this should then be our private ECCS key. Right now, this file doesn't exist, so that's going to fail every time. So we should maybe edit that and move a file over. The only reason it doesn't exist is because we currently set that's not in this directory. So I'm just going to set it to this directory and then create one. We knew the size of that key, so we can actually go back and find it. I don't think I copied it over to 5. Oh, I did. Nice. So the private key should be 96 bytes. We could check to see what's in there, but we know, it's going to be no bytes. So we're not really sure what data is in there right now. There is a hint that we can actually identify for what data would be in here, but we're going to hold off on that for a little bit. For now, we're just going to copy over this file, and then we don't really need to copy it over, so we're just going to put garbage data in there. So let's just create a Python 3 test C print. We'll do the letter B this time, times 96, and store that into ECC P256 private.bin. So now we have a private key stored in here that's fake, but it is going to give us a representation in memory of what a private key should look like. Okay, close that one for now. We'll come back to that probably later though. Now that we've modified the config, we're going to have to restart all of agent. And the reason we need to do that is because main isn't going to be recalled, and we need the config to be reloaded so the private key is read into memory. I have to kill it from GDB if I can. There we go. Kill it. Just going to restart it and reconnect. Our breakpoint should still be valid, so we're just going to continue. We could check out the memory just to see if our private key was read this time. It appears not to have been. Still 4E. So let's come back to Ghidra. If we come down to read private key, maybe we need to step through this and see what's actually happening. It looks like it does a check to see if local 14 is actually set to 0x60. Maybe it's reading in right here all of the data. So if we check back at our file, let's tech LA on ECC, we can see that it's actually 97 characters. And that's because Python added the new line. You can change that by saying end, I think, to nothing. End line. There's a way to do it. Another way I'm going to do it, could do it, just do import sys, and then do sys.write that should, or sys.standardout.write. There we go, and then we check the length this time. It's 96. There should be a way to do it with print. I think it's end or end line or something, but neither of those worked. Now if we run it again, kill this, target attach, continue, check out this data in memory. We can see that we now have a bunch of B's in memory. So it looks like that's where our private key is stored. You may notice that a lot of these addresses are probably the exact same between the times we run it. I think they should be at least. Continue the first time. So 7FED28. 7FED28. The reason for that is when you're running QEMU user space, there's a good chance ASLR isn't enabled. I think some of the newer versions of QEMU have it. I think this version doesn't. I can't, but usually QEMU user space like this just doesn't have ASLR enabled because that's done at the kernel level, and this isn't emulating a full kernel. Okay, so with that done, we can continue through. We can fake send some data. Netcat in. We need to send a bunch of data. I'm going to do C's this time so we don't confuse our A's, B's, and C's. Or confuse both our A's from our HMAC and our data buffer. 511. HMAC key, we don't care about this function. We could actually delete this breakpoint and set a new one at, go to command thread, and set a new one down here at decrypt. Decrypt is going to be at 40151C. 40151C. Continue down. We hit it, so it looks like we were correct in the assumption that X4 is our private key. So if we come down in here, we can set this to ECC private key. So now that we know that that's our ECC private key, we can know that this is going to be there's a good chance this is going to be a ECC related function. So we can come in here and see socket buffer is going to be the first parameter. So we'll just call that buff for now. Param2 was our private key. Come back. This might be data out, and it looks like it's from a main map. So this might be, and if we check out this, it looks like some kind of value. Main map is probably misidentified within this function. For now, we're just going to leave it as it is. We could just say static value of some sort. So var2 static value. var3 was the buffer, so we're probably gonna, this is probably the buffer out. It's also used within this last function down here before the freeze or cleanups. I think these functions are. The reason I think they're cleanups is that they're called within the failure section, and they're all looks like valid or static sizes on stack variables. So I think these are all cleanup. I'm gonna call it cleanup 1. Well, they're all just cleanup, the same function. Cleanup. And since they're not called anywhere else, it's probably safe to just call them cleanup and not worry about them. So we have our private key coming in. Looks like static value at 2 plus 7 divided by 8 is used. Awstack 88 appears to be a stack value that's used throughout. It's also 20 character or 32 characters, 20 hex in length. Awstack 68 is also used along with 48. 48 appears to be 0x40 or 64 characters. 68 is also 20 characters. We can start walking through and identify the functions that are used within this. So it's nice to just follow these buffers through. So private key is set to the second value. Private key. Param1, we know that one's going to be static since that was accessed from the stack variables. Param1 is probably the out buffer since it's the stack value sent in. But the private key looks like it's not used until this shift part down here. But out buffer at static right here is used. There's a good chance this might just be zeroing this data out if it's already initialized. It looks like we just go through ifr3 equal to 0, what's less than the static value. ifr3 ending it with 0xfc. So since we know this is going to kind of be the same every time, we might just be able to step over it. So I'm now going to start stepping into this function. Step down. I'm not in it yet. This should be the static access function, I think. Because I think I'm one back still. I think we're right here. 22d8, yep. So we're going to go another function in. That one should just return the static value or a pointer to the static value. Yep. Looks like the static value is just this 80 or 0820 0001. There's also all these F's, but maybe that's not as important yet. We can step into this next function. I'm going to come over here real quick and turn that off. Step through. We're going to want to come down to this first function, see what's actually done within it. We're going to look for this branch and link. So we know this is going to happen at, or call ADB8, which happens here. It appears to have a timestamp in the first parameter. Maybe that should just be old values because 88 hasn't been set yet. So maybe this will be a zero out function or setting it. So we're going to save this address and just do next instruction. Actually, check out the static value. Looks like static value became 20. So it's either the second byte. I think it was the second byte was 0x20 because it went 08200001. Doesn't matter too much, but what does matter is that we want this. And it looks like it's going to grab 20 bytes of some sort and maybe just copy them in here. So we'll do next instruction, check out this data. Looks like it's all B's. At this point, it may be nice to know what part of the... There's a good chance that it's probably just the first part. Since, well, not a really good chance. It's a guaranteed chance that it's going to be the first part since it's just doing private key plus. There's a little bit of shifting going on, but this looks like to be that it's just doing a reversal. So maybe it's converting to big endian or vice versa, since we're usually stored in little endian memory. But what that matters is the fact that this is the only spot private key is used, and we know we're copying over private key, but we're only using the first 32 bytes, so can't do that. Private key temp buff, maybe? Not a great naming scheme, but it works. Yeah, I don't like that. Well, PK buff. I don't like the variable names being too long. But what's important to notice is that we're only taking 32 characters. And this matters because the private key, what really matters is only the first 32 characters. If you do some research into elliptical curve cryptography, the private key is, this kind of private key setup is going to be usually 96 characters in length, which includes the 256-bit private key along with the public key, which is going to be 64 characters. And we know the public key. We can go back to 5/private. You go back another directory. Change to 5/private. And we know the public key is 64 characters. And we actually happen to have the public key. So if we wanted, we could append this public key to the private key and just do 32 random characters at the beginning. That may be of use at some point, but right now it's not because we've identified only 32 characters from the private key are read anyways, so the public key would never be touched. But the private key will always include the public key within it. Now that we've identified that, the private key is copied and then sent into these other functions down here. We can continue walking through this function. Yeah, I'll go a little bit further in this part, or in this video. So we know ivar7 is going to be cvar1, which is going to be static value at 1, which static value is a character pointer, so that should also be 20. So we could probably just set this to static 0x20. So it looks like buffer at static plus 0x20. Oh, no, that's the second one. First one, we have buffer ivar6, that's also going to be static 20. Static under 0x20 underscore 2. Those should be the exact same value since they're just set directly right there. And that might just be Ghidra noticing that they're moving it between a different variable and try to fix it for us. But our buffer that we sent in is then done into this one. This is probably looks to be the exact same function above. Can actually just check. Looks like all three of these are the same function, so this appears to be a copy function. We could step through and identify that it's just going to copy it into memory right here. And lo and behold, they're all just C's. It might be shifting them around big endian style, just based on this shift occurring right here. Or it could just be combining it into, I think it's shifting it. It might not. It might actually be just combining it into D words and then moving it at once. I noticed that sometimes it just likes to do that because it might be slightly faster than doing byte by byte. Doesn't really make too much sense. So this one appears to be the first 20 bytes of our buffer. So buffer underscore beginning. I can't spell begin. I'm just gonna do beg. Copy at 2 appears to be beg plus cvar1 times 4. cvar1 was 0x20. Nope. It looks to be the first character at 0x at static. We could check that out, which should actually be 8 if I remember correctly. So 8 times 4 will still be 0x20, so this also is 0x20. I think the only reason this is happening is because buff beg is set to be 64 bytes instead of 32. If we change this, it might just do at buff beg 2 or something. It might not hurt to rename it, but it doesn't look to be using that offset ever again, so it appears to be using this as a solid 64. So maybe it's copying the first 64 bytes of our buffer and then doing something with them. This is going to be storing them into buff bag. Yep. Okay, so now we can follow the private key buffer. Comes down into this function, along with offstack32, offstack68, which is set into local 98. So this would be some kind of double pointer there. Static value is still used here, but if we step into this function, it appears that we're going to be diving further into the math. And I think with that, since we know this is going to be elliptical curve cryptography, before we dive any further into the elliptical curve cryptography math, I'll save that for part 2. Thanks for watching, and hopefully you continue on.